this computer.
Yeah.
Okay, we are recording, everybody. Thank you.
Okay, so all set. Thank you very much, everyone, for joining. Good morning, good afternoon, good evening. I think we got people from all around the world. My name is Pejman Shoeibi Omrani. I'm working at TNO as a senior scientist. I have a background in mechanical engineering and applied mathematics from Delft University of Technology. And I've been working on several topics related to the subsurface energy production systems, mainly focusing on production optimization from different type of systems, ranging from mature oil and gas assets. And since a few years ago, we are looking into geothermal assets and how new technologies, innovations can help the operational cost to be minimized. As said, I'm working for TNO. For those who don't know, TNO is a Dutch research institute for applied sciences. And within TNO, we are working on various societal challenges, which of course, energy and material transition is one of them, if not the biggest one. And within our unit, we are focusing on different energy commodities, on how we can make them available and optimize them for the society. So it's really ranging from subsurface production systems to hydrogen, to carbon capture, to industrial heat. So it's really a broad range. So I'm coming from the group which focusing on optimizing the energy production from subsurface assets. And the topic of my talk is about heat is on, the vital role of operational expenditures and strategies for an effective resource management. So the whole thing is, of course, the heat is on because everybody is talking about geothermal. It's a very hot topic. It's a topic that attracts a lot of people from, let's say, petroleum industry, from non-petroleum industry, from water sector. And also a lot of students are now looking into this topic to see if this could be, let's say, a future career for them. What my talk is about is it's not just that the heat is on, you want to keep it on. It's not just to make sure that we can get a geothermal well and we can finance it and then that's it. You want to keep producing from your geothermal system, mainly because of the security of the supply. And that's often not a very easy task. So I would like to talk about that. What are the challenges that might impact the word heat is on and how you can keep it on? That will be my talk. What I'm going to talk about today, I will give a very, very, very brief introduction to geothermal energy. I'm not going to go into the details of that. There are lots of things that you can read about it. You can follow. So I'm not going to, let's say, make a lecture about the geothermal energy. This is mainly just to give you a bit of a perspective. Why is it important and what is the type of geothermal energy system that is specifically in the Netherlands? We are looking into them as of now. I will give you an overview of operation and production issues in the geothermal systems and also a lot of flow assurance challenges. So for people coming from petroleum sector, this word, I guess, invented by Petrobras is quite a familiar term, how you can get this flow assurance challenges in the system and how you can actually mitigate and control them in geothermal systems. And you would see some similarities, you see some differences. So I would also talk a little bit about this. And in the end, I would like to go a little bit into how we can actually turn these operational challenges into opportunities for our geothermal systems. And I would like to wrap the whole thing up by a question whether actually geothermal is a sustainable energy source or not. And I would like to prove that with some facts and figure, and already to give you the answer, yes, it is a sustainable energy source, but wait till the end that I can also show you some figures about it. All right, so geothermal energy. There are various ways that you can actually categorize geothermal energy. This is a one picture that I kind of borrowed from my friend Alex Danielidis from University of Delft. And you can see the different type of systems from the left where you have mainly the direct use of heat. So these are the hydrothermal systems that you actually produce from a sedimentary aquifer. You utilize the heat directly, and then you just inject it back into the subsurface. And as you go further to the right, you start to see systems with much higher temperature and also higher energy content. So what's higher enthalpy that you can actually extract from these systems. And if you have, let's say, good reservoirs, you can actually, from these naturally fractured systems, already produce temperatures above 200 degrees, which are, these sort of systems are very good for power production. So you can actually couple it directly to kind of an organic ranking cycle systems and already directly produce power from this. But if your, let's say, reservoir is not up to the, let's say, characteristic that you were looking for, there are also this enhanced geothermal system that you can actually improve the permeability of your reservoirs in order to still get sufficient flow in the system. And there are other way of classifications as well, so based on the temperature, based on the enthalpy, but I think this just gives you a bit of a feeling that you can have systems which are directly being used for heating purposes, and you can have systems that goes for the power production. And often you see that sometimes there are power production systems which they use the injection water temperature as a kind of an additional heat for heating purposes. So then you kind of get it into a dual mode. So these are a way of a classical classification of the geothermal system. But of course, there are some new type of geothermal, like the advanced geothermal or even supercritical geothermal systems are coming. Some people even call them unconventional geothermal. These are really about, the whole thing is about how you can tap into this energy from the subsurface. And in this advanced geothermal system, so I'll take this example from Ever, a Canadian company, where they try to actually build this massive heat exchanger under the ground. And in that way, they don't have to deal with all this geothermal brine that you have to actually produce from the aquifer, which can contain a lot of, let's say, minerals and materials that can give you some headaches. So in this way, they try to make these advanced geothermal systems, or even this picture I took from Clean Air Task Force, where they want to actually look into geothermal potentials in the supercritical conditions. So you're already talking about above 400 degrees, above roughly 270 bars. So this is really, let's say, a novel way of looking into geothermal, because this sort of energy you can, in principle, find it everywhere. So depending on the temperature that you're producing, there could be different applications. So I really talk about water brine, and I talk about the steam system. There is a kind of a temperature range into this. When we look into this direct use, you already see temperatures limited to 120, 30, 140 max. And it can be used for space heating, for district heating, also for cooling and greenhouses. So these are the, let's say, the very famous examples of using geothermal as a direct use application. When you go more towards the steam system, then of course electricity production, or if you need a high-grade heat for some industrial application, then let's say the high enthalpy geothermal systems becomes very popular. This is just a bit of give you a kind of a view on what is the installed capacity and the produced energy of the direct use and the power in the world. So the source of the data is there, and actually my colleague Alex from University of Delft also gave a very detailed introduction to geothermal, which I will invite all of you to also watch that series from our GeoHackathon courses. What you see in general, that the share of the direct use is actually way higher than the power production in the system in terms of the installed capacity, but also produced energy. Yeah, you start to see that the produced energy from the power system gets a bit of a higher share. That's mainly because of the fact that more or less your geothermal systems for power production, they just running 24/7. And that's very different than the direct use systems, which are quite demand driven. So if you don't have a heat demand, then more or less your production, you just ramp it down. Otherwise, you're paying quite a lot of money for getting the asset up and running, but there is no demand for it. For the power, is different. It's just connected to the grid, and you can produce 24/7. So the load factors makes it into this graph that actually the share of the power production starts to kind of ramp up a little bit. Again, a very nice source of reading is this website, Think Geoenergy, which every year they publish this top 10 geothermal countries. And if you see over here from the power production, you see almost all the countries which are really leading this, starting from United States, Indonesia, Philippines, Turkey. And it's really, let's say, an impressive list to see how these countries are growing into their geothermal power production. And from the other side, if you're looking from the heating purposes, this is the map presented by EGC, which shows, let's say, the current installed capacity and the locations where you have geothermal for heating. So just to give you a bit of an idea, we have currently more than 360 geothermal district heating projects and systems around the world. And this is expected to also be triple in the upcoming years. So why actually geothermal for heating is important, why it matters, how it can help us to reach our decarbonization goals. There is, let's say, just to give you a bit of a European perspective, if you look into the percentage of the energy consumption in the different sector, you see that actually, for instance, if you look into the households, around 25% of the energy is actually European-wide is actually used in the households. And zooming a little bit into that, then you see that the space heating is responsible for more than 65% of that energy consumption. And for a space heating in the houses, you do not need a very high temperature. Already what you can produce from the geothermal is actually sufficient to provide this. So if you can actually, instead of using the current way of providing space heating, which is based on fossil, if you can decarbonize it with the geothermal, you're going to have a massive impact in the share of the fossil fuels for space heating. So I would like to zoom a little bit into the Netherlands because I would like to also start to talk a little bit about the current operational challenges. This is the current status in the Netherlands. It's in Dutch. I'll just take you through this. This geothermal market currently in the Netherlands is really growing. So yeah, the heat is on also in the Netherlands. Currently, we have around 36 geothermal systems, and mainly for the direct use. I have to say, only for the direct use heating application. And the total production is around 7 petajoule. And traditionally, this system has been used for the horticulture sector, so mainly for the greenhouses. And now you start to see that there are lots of plans to extend this also to the built environment, so provide heating to the houses, also cooling to the houses using geothermal as a source. And this is mainly because we need to also decarbonize our space heating, as I showed in the previous graph, and that will have a massive impact on the overall CO2 footprint of the energy system in the Netherlands. The type of systems that we are using in the Netherlands, this is a bit of an overview. So on the right that I show you this geothermal production, so mainly for the production purposes, and you see the other 3 types, which are also for the thermal energy storage. What is very important to know that in the Netherlands, we have a geothermal gradient of around 30 degrees per kilometer. So it's a relatively modest geothermal gradient. That means that, okay, if we look into the current conventional geothermal systems in the Netherlands, between the depth of 1.5 to 3 kilometers, you're expecting to produce something up to 85, 90, 100 degrees. That's the kind of the range that you can produce. So there's going to be all hot brine system, no steam will be produced. And since let's say the conversion efficiency is pretty high, since you just need a heat exchanger to extract the heat, then these systems are getting very, very popular in the Netherlands for the 2 sectors of horticulture and built environment. This is just some numbers to give you a bit of an idea on the type of the system. So just to kind of give you a bit of a feeling of the configuration of the geothermal plants, there is a producer well and there is an injector well. So in this way, you have this pair, which is called duplet. They're connected to the same aquifer, so you don't have them that, for instance, one is producing from a deeper layer, and then the other one is injecting at the shallower layer. So everything is actually in the same aquifer. You preferably do not want any fault or sealing between the, let's say, the two wells, and the whole idea is to produce the hot water, extract the heat, but of course you would like to filter the water. There might be some corrosion issues that you want to have inhibitor injection, and there will be gas, which I'll talk about it as well. And after that, when you have the cold water, you just inject it back into the reservoir. I already talked about the geothermal gradient in the Netherlands. Give you a bit of a idea of the volumes that have to be produced. We roughly talk about 120 to 400 cube per hour production. This is quite high if you compare, for instance, to oil wells, and that's because you need to produce much more heat to supply the demand. So looking into the energy content of the gas and the hot water, so the production rate has to be high in order to make the project economic. Here I'm showing the salinity as a function of the depth in the Netherlands. So just kind of to summarize this, yes, it's very saline water, and it contains a lot of different minerals. I'll talk about it in a few minutes about what sort of challenges you can expect by having such a high salinity. And maybe one point also about this configuration. So it's just a bit of a schematic view. Actually, in reality, you do not have these wells to be vertical. So more or less on the surface, they come to the same point. And in the subsurface, you have them deviated and inclined wells, often by like 45 degrees. And they design it in such a way that the distance between the producer and injector will be between 1 to 1.5 kilometers. So in that way, you expect the breakthrough time would be in the order of 30 years. So that's a little bit some kind of a rule of thumb for the design of these geothermal systems in the Netherlands. But what happens during the production? What happens is actually you produce a hot water. That's this hot brine with its salinity. It's actually in equilibrium in the reservoir already for, let's say, a million years. It has been there. Now you kind of produce them. You change their temperature as they're coming to the surface. The pressure is changing. On the top of the surface, you actually might, for, let's say, safety reason, just degas it. So if there is some by-produced gas, you want to take that out. And then you change the temperature, and then you put back the cold water into the reservoir. So there are a lot of pressure, temperature changes happening in the system. And as a result of this, actually the equilibrium of the brine starts to change. And that can give you some issues. And that's going to be the whole talk that I'm going to give today. So this is about the very important thing for the operation of this geothermal system. But next to that, one different thing also about the geothermal, maybe compared to the oil and gas system, is that these direct systems has to meet the demand. So they are actually driven by the demand, and demand of the heat is very variable. Already you see this seasonality in the heat demand for this famous, we call it the bathtub curve, that in the summer you don't need much heat. And yeah, you need to design a system, you need to design your facilities to actually deal with such a, let's say, variations in the system. And often geothermal, you look at it as a kind of a base load. You don't want to change it that often. So how are you going to deal with this? So operator has to deal with these issues of changing conditions on their brine, and that can give them a lot of headaches. While they have to also meet this heat demand, and it can give a lot of, can be coupled to all these flow chemistry challenges like scaling and corrosion. So a lot for the operator to take. In this case, it's not just let's maximize the production. Actually, you have to meet the demand. That's very important. So combining these two, I always have this cartoon that to say, okay, this is the kind of a daily job of a geothermal operator, has to find the optimum of what's the best way to operate the system to meet the demand, not getting any of these flow assurance challenges. But as soon as they find the optimum, already the next time step is coming, which means that they have to go to the next optimum control. So it is a very, let's say, going to be a tedious job for the operators, and they have to really find protocols and methods to help them making a better decision. Already talking about the heat demand, well, already on design phase is a pretty challenging question. So imagine you have such a heat demand. How are you going to design your geothermal system? So you want to go with the geothermal as a base load. What should be the minimum that you can provide to you? Are you going to have a storage potential? You have locations to actually seasonally store this heat. But what are you going to do with the peak loads? And if you do your peak loading with some gas boiler, of course, there will be also emission penalties for the work that you're doing. So how can you bring all of them together to supply this heat for the security of the supply? Do not have any downtime, but the initial sizing of your system should be already efficient to meet this heat demand for a district or for, let's say, a set of greenhouses that you're supplying heat to. So it's very difficult, but often if you talk to geothermal community, the biggest challenge is always about investment costs. It's about drilling costs, completion costs. Do we go single barrier or double barrier casing? What sort of material do we use? Everything is kind of driven by the investment. Everything is driven by the initial cost, by more or less the capital expenditure. And often the operational expenditure is being forgotten. But if you have a very beautiful geothermal system, which you think, okay, I've studied the subsurface, I know I have a very good aquifer, I can access this heat, I can produce. But if tomorrow, for instance, you get a sand production, you have to ramp down your production. You even have to stop your production. So sometimes those operational issues and the cost that will be associated with it, that they could also be a killer of the business case. And yeah, just for that, I always have this, again, another video as let's say, someone who always tries to think about the future problems. Do I get a breakthrough in 20 years or 30 years? And actually this fox here is actually your operational problem. They're just next door, you know, like you get a corrosion, you get a leakage, that's it. You have to stop the production, you have to do a costly repair. And yeah, you can't really supply that heat. So don't forget about the operational issues and how to deal with them. And what I'm saying is also supported by the numbers. So this is a survey that we have done in a program called Warming Up. This report is actually publicly available, where we collect a lot of information from the CAPEX and the OPEX of the geothermal systems. And we made some comparison between these operators. And one very interesting thing is we have two operators here. All the numbers are normalized because of the confidentiality. What we have is that we have one case that the operator, their annual OPEX was around 8% of their total cost. The total cost is actually your total CAPEX plus, let's say, the annual OPEX. So this is a quite high share because you expect that your OPEX should be roughly, let's say, 3 to 5%. We had another operator which had only 3%. So that's the operational cost was really, really lower compared to the other operator. And what you see is that the second operator, they spend much more money for their design of the wells, for the sand control, for the materials that they have chosen for their casing and the surface facility. So for much higher CAPEX, and then they can already see that it's kind of paying off in much lower OPEX that they have in the system. And these are not just because that the CAPEX is higher, the percentage is going low. If you look into the absolute numbers, you don't see numbers, but if you look into the trend, you already see that even though the CAPEX is higher, but in also absolute term, their OPEX was lower. So this is very, very important to know that if you take the OPEX into account, maybe you go for a higher CAPEX, but that ensures that over the longer period, your system will not be interrupted by some of these operational issues. So I would like to give you a bit of for the rest of the time, I would like to take you through some of the items with respect to the operational issues. Here you see the overview of the cost, the operational cost that the different operators are dealing with. So the first operator, of course, had quite a large cost because of the production wells and the issues that they had with the corrosions in the wells, and the second one because of the much better materials they use. That part was much smaller, still having the pumps, which contributes quite a lot to your operational cost. I would like to go to some of these flow chemistry challenges in the geothermal system, just to give you some ideas about what sort of issues these operators are dealing with it. And of course, the first one is always coming to the top of the list is corrosion. So this is very important because you want to make sure that the integrity of your wells and facilities is there for at least 30 years. But production from geothermal reservoirs is challenging. You have all the conditions that you need for corrosion. You have a salty brine, you have high temperature, and also you have dissolved CO2, sometimes even more than 10 mole percent. So you have to be careful about this, and you can get different way of corrosions in the system. Yeah, you see the, let's say, this cartoon here of showing the different type of the corrosion. Currently, the most important, let's say, way to mitigate and control this is, of course, monitor the corrosion. And inhibitor injection is also one of the very regular practices for controlling the corrosion. We see now there are more developments in the market to go also for GRE liners. So in this case, you do not have metal contacts with a brine in the production well, and then you can minimize your corrosion risk quite a lot. What's very important, if you look into most of the early wells in the Netherlands, they have been designed with a single barrier. So this is, let's say, an example of a completion. There is no production tubing or liner. There's just a single barrier. So you actually start to produce your salty brine at high temperature in the production well. There is just a single barrier, but also initially most of these wells were designed with carbon steel or very low alloy steels. So that already know that why corrosion was kind of an issue in this case. And okay, you can inject corrosion inhibitors, there's no problem with there, but the rates are high. So even for injecting only 5 or 10 ppm of corrosion inhibitor continuously, in the end, yearly, you're going to pay a lot of materials because you have to kind of provide 10 ppm to 400 cube per hour of the brine. So that those costs, eventually you have to see, oh, does it make sense? Maybe in the beginning, I should have already gone with much better material for my casing. So always make sure that even if you're designing a new geothermal system, you have to be careful about these operational issues and already take that into account during the design phase. And if not, always monitoring and way to mitigate it is something that you have to keep a close eye into this. The second problem is the scaling. So scaling is actually the part because you have, let's say, this salty brine with different minerals in this. And at a certain point, because you change the condition, you kind of, at some conditions, you make it very favorable for these minerals to come out of the solution. And you have different type of scaling. You have carbonate scaling, you have sulfate scaling. And if you, in principle, look into all the geothermal systems, so here I show the calcite and barite, let's say, equilibrium at the, what we call an infinite dissolution. And in the salty, let's say, water, you already see that you go way above the, let's say, the saturation line. So the chance of getting this sort of carbonate and sulfate scaling in the system, if the minerals exist, is pretty high. Currently, mainly with the corrosion inhibitors, they have been controlled. The carbonate scaling, you can also inject CO2 to modify the pH and deal with that. But you already know that, okay, modifying the pH by injecting CO2 in the system to deal with the carbonate scaling means that you increase the risk of the corrosion. And you have to find some optimal. So in the end, you inject CO2, your scaling problem is gone, you get a corrosion issue, and then you have to inject the corrosion inhibitors. And no problem, you can control it, but these are all costs. The other type of, just get a bit of water. The other type of scaling is actually what we call the heavy metal scaling. So this has to do with having some dissolved lead or copper in the system. I show you some of these low enthalpy geothermal systems in Denmark, Germany, and Netherlands, and looking into the concentration of the lead which they are producing. But one thing which is very tricky about this type of scaling is that if you get this scaling in the system, then this deposit actually will create a medium which will lead into the galvanic corrosion, because you will get two different metals contact. So when you get the lead being formed on your metal, you get lead on top of steel, and that can lead into the galvanic corrosion. So it's a very tricky one to deal with. Also common in some of the geothermal reservoirs. Yeah, inhibitors could be a solution for this, but you have to also carefully select this. But it also has to do with how you're going to actually design your pipes and select the pipe materials. There are ways to, you can also filter, so you can have some particle filters as well for this. and some innovations going on in this venue, which in few slides I will also show you some of these innovations. The other issue is NORM, so the natural occurring radioactive materials. And this is not a very new problem in oil and gas as well. There we also see a lot of this NORM issues. The only difference here is that the volumes that we are producing in geothermal, they're very high. So if you can find a way to even filter these materials, then the amount of material that you have deposited on the filters, they exceed the kind of this maximum concentration that you're allowed to have, and then the disposal cost and the treatment cost will go really high. And just to make life even more difficult, this back in 2018, the maximum allowed radioactive concentration has been minimized by a factor 10. So from 100 becquerels per gram, it has been reduced to 10 becquerels per gram. And that just makes it even more costly, because then the deposits, well, it's still the same brine, still contain the same amount of, let's say, lead-210 or radium-226, and that would just makes it more difficult. So this is also an issue, which of course, any innovation in this way on how you can mitigate it, keep it dissolved, or do something with the filters is always appreciated from the sector. And this is not the only challenges. There are other challenges as well. And just looking into the time, I can't go to all of them, but just to list them, there are sand production issues, particle migration, especially you see these issues in the shallower reservoirs in the Netherlands because of the unconsolidated sand. And if you do not design your completion well, if you don't have any sand control strategy, then in principle, well, you have to ramp down your production, or well, every week you probably have to take kilos of sand from your separator and your surface facility. So this is a very important one. Injectivity decline as well. So this could be actually a mix of different things that can lead into the injectivity decline. It can be induced by the microbial activity. It could be because of scaling. It could be because of the particles. But there are examples of geothermal system that, because of the injectivity reduction, they have to also ramp down the production. And that means that the overall performance of the system had to be dropped. And one other last issue, operational challenge, is actually the gas production. So you can also get gas to be produced with your geothermal brine, depending on the type of gas. So whether it's CO2 or oxygen, which can give you corrosion risk, or if it's a natural gas, so you have to treat it very well. You have to be careful with all the safety issues around this. So it's not that, let's say, an unknown problem, but how to manage the by-produced gas is, of course, a very, very important operational. So this is, let's say, a bit of a side remark that I would like to refer you to this project called Perform. This was a European project where a lot of the issues have been listed. A lot of inputs from the sector came here, and we provided a best practice on how to deal with the scaling corrosion issues in geothermal systems and what will be the best protocols to sample your brine. So please go to this website as well if you're interested on this topic, and then access the guidelines, where there's a lot of useful information in this system. Another thing is about these downhole pumps. So downhole pumps are also quite crucial in the geothermal system. Their costs are high, but these are also the heart of the geothermal system. So if you want to produce water, you need to have this artificial lift in most of the geothermal reservoirs around the world. But they relatively have, well, short lifetime might be a bit of a too strong word, but I would say shorter than expected. And we have to look a little bit carefully into, okay, why do we see shorter lifetime in these geothermal wells for your ESPs, for your electrical submersible pumps, compared to what you see, for instance, in the oil wells? And look into it a little bit, deep dive into it, and better understand what is actually happening in the geothermal, which makes it different than oil wells, and can we find some root causes for these more frequent failures? A lot of, let's say, research was done in this topic. There is a very nice list of things which has been found that whether it has to do with the environment of the geothermal, so what you're actually producing, human environments, and also design operations. Some highlights of this, I'll bring it into my next slide. But in general, you see that on average, these pumps are running around 2 years. This is coming from the data that have been there. Also, there are cases which these ESPs were only running for, let's say, only 9 days as well. So it's very important to look a little bit into the depth of this. For the time purpose, I would like to just go to this slide. This is some potential reasons why these geothermal ESPs have a shorter lifetime. And one could be fluid composition. So you have a very nasty geothermal brine composition with all these ions and dissolved gas that they can give all sort of corrosions and scaling issues, which reduce your pump performance. In general, if you look into the geothermal systems, their installation depth compared to oil wells is much shallower. So if you have a well of 2 to 3 kilometers, these are the, let's say, the ESP depth installed in the Netherlands, which goes from, let's say, around 300 meters to 1 kilometers. So what happens is, of course, if you get this startup and shutdown of the system, the temperature that the ESP will see will be quite a broad range of the temperature. So this can potentially lead to some thermal fatigue and material failure. So this is, of course, important one. There is no sign of this, but it's always good to take into account that there are differences between geothermal ESPs and oil and gas ESPs. We are producing high volumetric flow rates. That's already explained that, of course, the energy content in the hot water is very different than oil and gas, so your volumes are high. And imagine these high volumetric flow rates are combined with temperature and high salinity water, so it becomes quite challenging. But one very important thing is this seasonal demand and the flexibility that you have in your geothermal system. So these pumps, of course, have a recommended operating range. But if you look into those recommended operating range, they are still smaller compared to the demand that you have in the geothermal, you need from the geothermal system. So your pump has to go kind of beyond the operating range, and that's, of course, not recommended. And this can be kind of a initiation of the failures in the system. And the last one is less experienced operator. So this, of course, again, is quite a, let's say, a strong remark, because there are also a lot of people from the petroleum sector with experience, which goes, but often how to deal with this sort of systems could also be just new to some of the operators, and we have to also acknowledge this. And if in any ways operators can be supported and assisted to make a better decision about how to deal with the ESP, how to increase the frequency, reduce the frequency, that can always be helpful. And there we see a big role also for the digitalization. So how you can use digital technologies, how you can use predictive models, show them in real time to the operators to say, oh, I mean, you're getting into an off-normal event, you're getting into an anomaly, your pump is about to fail, so do something about it. And this is, again, also a case study which we have shown for an ESP system in the Netherlands, that this ESP actually has failed in January 21. And we've just shown, okay, what if this operator would have some models which has been trained on their historical data, and they were just running in real time in the system, and give them some ideas about how currently their ESP is performing? Can we actually detect some of these failures before they happen? Because then in that way, you can provide that alarm to the operator. And we created multiple models, which I showed 3 of them to you. So motor temperature of the pump, ESP vibration, and ESP power. And what you see that already, that if this is the point of the failure of the component, already the first signs using this model can be detected even 6 months before they happen. So if this operator had this model to monitor the ESP vibration based on the historical data that they had, they could detect that this ESP vibration already a few months before the failure is not normal. So they have to do something about it. The least you can do is actually you can order the pump, have it in the warehouse, and then as soon as it fails, you can replace it. That could be the minimum thing that you can do. But yeah, if it just failed at this point and you have to wait, order a new pump, again, there will be a lot of downtime. That is something that you don't want. All right, so I've showed you a lot of challenges. Of course, the big driver is cost, because you need to ensure that not only the high capex is important, but operational cost could also be a problem, and operational issues can be a problem. But most important thing for this geothermal, which we use for the heating applications, is that the infrastructure is also needed. So you might have a very good reservoir that you can produce hot water with high rates from this, but you need infrastructure to kind of transport this heat for the end use, whether it's in the greenhouse or whether it's in the house. You need to have that infrastructure. So the demand side and how to kind of transport it there is very important. But of course, from the cost side, and when today I talk a lot about these operational issues, we see that innovation could be very, very important here. So with innovation, you can find ways to reduce this cost, make the geothermal system operation more smooth, and in the end, help to accelerate this geothermal energy in the sector. We work on several innovation. I think, again, for the time reason, I will be very quick on this. I already talked about these lead deposits, which if they go into your system, whether you get it, let's say, in the heat exchangers or in the pipe system or somewhere in the well, as soon as they deposit, they would lead into corrosion. So one of the innovative ideas that we work and perform 2 projects with some of our partners in Denmark and Germany is that we're going to come up with a new filter technology, which is going to extract some of these ions. In this case, specifically, it will be lead, barium, and copper. And you're going to put it at the point where you want to kind of preferentially absorb these materials to kind of protect the downstream components. So in principle, if you see where you have can get more scaling and corrosion issues as a result of lead, if it's on the cold side of it, what if you actually deploy this filter on the hot side of your heat exchangers to kind of extract all of this? And that means when you do the cooling in the heat exchangers, you do not have to worry about any scaling and corrosion issues. This is gonna give you big savings with respect to corrosion inhibitors, and also the potential risk of, if that corrosion happens anyway, there will be big costs for, let's say, changing your heat exchangers and the surface facilities. So here are like one of the innovative approaches that you can also minimize the chemical footprint of your system by injecting less inhibitors or even no inhibitors in the system. I will also skip this. I'll go to another innovative approach is the project where we are looking into using, so in the previous project, we were thinking of minimizing the use of chemicals. In this project, we actually want to add an extra chemical in the system, but we see also some very positive response in terms of the cost reduction. And here we are looking into the use of drag reducing agents. So these are surfactants or long molecular chain polymers, which with a very small amount you can add to the system, and you can get a huge reduction in your pumping power. So this is a very well-known concept, and now in the project called DRAGLO with the consortium, we are looking into using this sort of technologies to minimize the cost. And if you have already an existing geothermal or district heating system, you can just inject these materials and directly minimize your pumping power. But the interesting thing is that if you want to design a new system, you always go for the large casing and pipes because you want to minimize your pumping power. But if you can go to one smaller size casing on the pipe, what can actually happen is that you can keep your pumping power the same by injecting this DRA. So already you can also think about capex reduction by minimizing your drilling size, drilling rig that you need, because if you go to the smaller casing, you also need the smaller drilling rig. You can go to smaller district heating network pipes, and in that way, your overall cost will be minimized. All right, so some examples of innovations here as well. Again, this is a very nice one. So we show that actually in this case, we can minimize the pumping power by actually 70% using some existing surfactants in the market. All right, I would like to end my presentation with this slides about whether actually we have all this operational cost to produce heat, which we also saw that okay, the value or the price of the heat is way lower than gas. The energy content of that is also lower. So we go through all this hassle to actually decarbonize our heating, but actually is geothermal a sustainable source? And the argument could be, well, you have pumps in the system. The pumps are consuming a lot of energy, and so far the electricity grid still is running by let's say the share of the fossil for power production is still pretty high. So that's the, let's say, one way that you contribute to the emission. The second is that you're also producing a lot of gas. You're producing CO2. In the Netherlands, we're also producing natural gas. I can show you the share of the ratio of the natural gas to the CO2 for the different countries. And you can see in the Netherlands, there is a large amount of natural gas which is being produced by the geothermal fluid. And the ratio is also high. So in some of the formations in the Netherlands, for every cube of the water that you produce, you also produce 1 cube of gas. So you're roughly, if you're producing 200 cube per hour of brine, you're producing 200 cube per hour of gas. So is it actually sustainable? And okay, for that, you always have to have some measures. We took 2 measures, which one of them is based on the climate agreement and the other one is based on the Heat Act, which says, okay, you have to kind of go with this criteria of roughly between 20 to 25 kilograms of the CO2 per gigajoule of the energy that you produce. And if you can achieve that by 2030, 2050, then that's the point that you can say, okay, yeah, then we kind of meet this agreement that we have. So we look into some of these geothermal systems in Europe and also around the world, where on the left you see mainly the low enthalpy system, and you see the Dutch systems next to the systems in France, Denmark, and Hungary. And these are all based on the public data, so maybe there are some pluses, minuses here. But we look into the emission which comes from this system, which the light green is actually the part that is the power consumption of the pump, and then the dark green is the part which comes from the formation gas which is being produced. So you already see that maybe in some countries the formation gas is really high, but in general you're expecting between, something in the order of between 5 to 10 kilograms of CO2 per gigajoule that you're producing from the geothermal systems. And if you look into the kind of a bigger perspective, where you also bring the geothermal power production sites and compare it with coal, oil, and gas, you see that the emissions of the low enthalpy geothermal systems are pretty low compared to oil and gas systems. There are still some geothermal plants in the world that are producing, looking into the emission factor might look high, but of course there is also quite a high share of natural gas and CO2 which is being produced from this well. So please take this with a pinch of salt. If you have to kind of normalize it based on the energy content that you're producing, still these values would also be much lower. So compared to what we get from the fossil sources, yes, it is a sustainable source. And this will be my last slide, because I would like to just not talk about only geothermal system. In the end, everything is demand driven. So if you want to look into your emission, you have to look into the emission you make from the source, but also from the transport of the heat from the source to the demand. So in this case, we also look into the case where you have a geothermal as a source, but the heat has to be transported, and you have some boiler on the way to make sure that those peak loads are also met. And in that way, we look into the full system from the emission perspective. So here you see the different reservoirs over the years, and we have these green ones, which are the geothermal contribution. In gray, we have the part which is actually the boiler, so the additional heat that in the network that you need. And then the orange one, which is the heat losses that you would expect in the system. So you need to put additional energy to meet that, to kind of compensate for that loss, and that also contributes to your overall emission. So if you see this, it seems that since we expect that the share of the power production, and actually the share of renewables in the power, will grow very fast in the Netherlands, the part which is actually responsible for the power consumption of the pumps in the geothermal system will be reduced, and that's already can significantly contribute to minimizing the emissions from the systems. And in this way, if we continue by the year 20XX, which I hope that will be 2050, yes, we're gonna go with all these requirements of the climate agreement and the Heat Act, that yes, this will be a sustainable source. But of course, take one of the assumptions that we had, that we say, okay, this additional energy required in the network would actually be by a gas boiler, and that has been kept constant. Of course, your demand is evolving, but most important thing is that you would look for alternative methods to provide this additional energy. Could be maybe biomass, could be electrical heating. So there also, this value would also change. So for taking all this conservative assumption, we still see that geothermal and the district heating are sustainable source, and they're going to contribute to the decarbonization of the heats. So with that, some summary or take-home messages. I'll start from the end. Geothermal energy is a sustainable source for heat and power. I didn't talk much about the power, as it's not really also the focus in the Netherlands. So I wanted to deep dive a little bit to the type of system you see in the Netherlands, give you a little bit that perspective from the heating and direct use application. We see innovation is very important, because actually this methods to harvest this geothermal energy and heat, they already been around, especially for the type of system that I've shown already. There was this interesting remark that, yeah, in principle, they are high water cut oil wells. Yeah, so there's just this sort of system. Yeah, in oil and gas, we are very well get used to this sort of system. The production rates are higher. The chemistry of the brine is different, but the technologies to deploy this heat is already there. The most important thing is cost. So if you can have innovation to minimize that cost in any way, this is very well appreciated. And of course, the last remark will be about the optimum exploitation of the geothermal energy, that is not only driven by the capital expenditure. Operational expenditures are very important. You have to take that into account. You have to know them very well and try to find ways to minimize that as much as possible. Even make them fully autonomous. If you have very nice materials, if you control everything, you can even make them fully autonomous and make them provide your base load perfectly without much hassles. So that was my presentation. I hope I could give you some ideas about some of these operational challenges, but most importantly, the importance of these operational challenges and how to deal with it. Yeah, if you have any questions, I'll be more than happy to take them. And you can always contact me on LinkedIn or send me an email if you want to have a detailed chat about these topics.
Right, Pejman, thank you very much. We've already got quite a few questions. Graham was the first one. Do you want to unmute yourself and ask the question direct, or shall I just read it from the chat box?
Well, you could read it from the chat box, but I had two questions. One is the amount of power that's used in the pumps, which you almost answered in your presentation. And the other one was about the gas produced, the methane. Can the methane be used? How much methane is produced? Does the methane reduce as you circulate water around?
Yeah, a very good question. So the pump power is, of course, is also driven by your production rate and the sizing that you have. So roughly, you see these values that can vary from, let's say, 0.5 megawatt to, let's say, 1.5 megawatts. That's the range. So there might be lower and higher values, but just to give you a bit of a feeling whether it's like 100 kilowatts or it's 10 megawatts. So that's the bit of the range that you're dealing. But of course, you would like to minimize them. So if you go for, let's say, more efficient pumps, or if you go for the larger tubings, then you can also save quite a lot in your pump power. There are also some which has a lower consumption. So that's one thing. And the second was about the methane. So yes, the methane is also in some of the sites being utilized. So there is also few of the sites which are using combined heat and power, where they kind of extract the natural gas from the separator. They take it into the CHP unit, and part of the power consumption of the pump, they could even also just directly get it from the natural gas that they produce. So it's already being utilized in that sense. There are already examples of that in the Netherlands, but maybe also in other parts of Europe.
As you're circulating gas round and round, does the amount of gas that comes out reduce over time?
Over time. So the thing is that, yes, I think somewhere in the presentation I mentioned that the breakthrough time, you're talking about 30 years.
Yeah.
So I think it's difficult to make any guesses around that. But I think except for one system in the Netherlands, all the systems, they have separators. There is only one system in the Netherlands that they keep everything under pressure and they have no degassing. So the gases stay dissolved. Some gas maybe still will be in the gaseous form and they just inject it back into the reservoir. But yeah, for most of the system, they just degas it. They keep some CO2 in the solution. So they try to, for that calcite problem, keep some CO2 in the solution. But yeah, most of the gas will just be utilized.
Yeah, it's quite common in Holland to have a boiler for the off gas. So yeah, the gas is not wasted.
Yeah.
Yeah. Okay. The next question came from RA. Do you want to unmute yourself and ask about single barrier? RA? Okay, so the question was about single barrier. What are the safety environmental considerations? Brine is a lot saltier than near surface groundwater, plus unexpected gas bubbles or slugs.
Yeah, so very good question. That's the whole reason that since a few years ago, there are actually some guidelines proposed by Geothermal Netherlands organization, which is a branch organization for the geothermal operators, where they kind of put that thing in perspective. The single barrier is not a good idea. There are a lot of safety risks, integrity risks, and if something goes wrong, of course, the workover also will be very costly. So for that reason, yeah, single barriers. But there was a reason that they have been designed like this, because they wanted just to maximize the surface area for maximizing the production with the minimum frictional losses. So that's the main reason. But of course, because of easier ways to monitor the integrity of the well for this environmental risk and things like that, of course, none of the wells will be single barrier. There will be a production tubing or a GRE liner, and there has to be a kind of a monitoring plan submitted regularly. So in that way, they try to do this. With respect to unexpected gas bubbles and slugs, it's not of that much issue, to be honest. At least again in the Netherlands. So there are other cases in Europe which there are slugging issues, but in this case, you need to have a kind of a critical fraction between your gas and liquid to actually initiate those slugging. And since most of these wells are kind of operated at a higher surface pressure because of the minimizing of the calcite problem, you don't expect much slugging issue on the surface.
Okay. Akos, are you online?
Yeah, thank you very much. Great presentation. I really enjoyed. I just have a quick question on slide number 21. There was a picture. Maybe you could explain a bit what was this plugging material? Is it some fines together with some microbiological product, or what do we really see there? Yeah.
Yeah, so again, you always see kind of what I call it, the kind of a soup of issue over there. So I mean, there are cases that you see, let's say, a lot of clays and the particles and sand kind of being clogged. But also, for instance, there have been tiny amount of oil also has been observed in one of these cases. And if you bring them together in a kind of a filter, then you start to see this sort of, let's say, muddy shape structures over here. So that's that. Again, there are lots of causes can be for this this sort of clogging, and often they just combine together. So that's a bit of the issue with this, let's say, clogging.
Okay, thanks, Pejman. Marius, do you want to ask your questions about PCP pumps? No, maybe not. Okay, so were PCP pumps considered? Metal rods are already developed and available on the market.
Yeah, so this is an excellent question. So, of course, PCP, jet pumps, or even gas lifts, so different. I mean, if you look into the artificial lift portfolio, you would see quite a broad list of possibilities. I mean, yeah, let's face it. And at these high rates that we want to produce in geothermal, ESP is the most efficient one. So all the other pumping mechanisms that you want to think about, or if you want to go for a gas lift, eventually you're putting too much power in the system, and that's not going to be economic. So I think for these systems, ESP was chosen, and if you look into the economics, they make sense for these high rates. For much higher temperature applications, one of the very common type of pump is also line shaft pumps. So in that way, you kind of protect all your motor and electrical component on the surface, and you just kind of transfer the power to a shaft. Still on the vertical side of the well, you can utilize this maybe for the built environment, and doing it in the urban areas might be a bit of a difficulty because of the noise generated. But yeah, I think these things has been looked into, and still ESP is the most efficient one.
Okay, thanks. Alwyn, you've got some information to share and potentially a question.
Yes. First of all, Pejman, this was a very good presentation, very engaging, very insightful. I was happy that you were able to bring out the alternative of GRE, or fiberglass lining of steel tubing or casing used in geothermal wells. I just wanted to add, for the interest of the forum, that fiberglass has its temperature limitations with regards to geothermal applications. I know we've supplied into the Netherlands, but you would only be able to rely on fiberglass for temperatures within 145 degrees Celsius. And I think it's okay for me to announce that very recently at an AMPP, which used to be formerly NACE event here in the US, I introduced a thermoplastic lining system, which takes lining of carbon steel into the 500 degrees Fahrenheit plus regime. So that solution's out there for anyone who's studying alternatives to the exotic steel pipes that are typically considered for geothermal well designs. I just wanted to share that information in this forum. And thanks for giving the opportunity.
Yeah, no, thanks a lot for sharing this. But maybe also of interest, also in one of our laboratory, which is in Rijswijk, it's called Rijswijk Center for Geoscience. We also made a pilot for a GRE well for the thermal storage application. So that's also one of the things that with some of the, let's say, companies in the Netherlands, we have made this possible. And now currently we also have all these fiber optics and distributed temperature sensors, which we would like to monitor the whole subsurface as well. But we definitely see that this GRE is now picking up very fast, and there are already, let's say, examples of the GRE lined geothermal wells in the Netherlands. So that's also already existing. And thanks a lot for sharing that.
Right, Pejman, talking about sharing, we're recording this session, and we will share that. And we can also share your slides as well, correct?
Yeah, these are all public material, so I can make it available to all the registrants.
Right, and then Daria, I believe you're next. You want to unmute yourself?
Hello. Thanks a lot for the presentation. It was really interesting, lots of useful information. Thank you very much for your time. I understand that it might not be your area, but maybe you can guide me in the right direction. I'm wondering about regulations of the geothermal energy in the EU, because I was reading on the subject and I found that there are two types of overlaps in this area. First, between pieces of legislation that are usually applied to the petroleum industry. Sometimes they do apply to the geothermal, sometimes they don't. Also, there is this hierarchy between the national law and the EU regulations. What overrides what in which country? So it's really very complicated legislative field, and I would like to read more on this topic to get more clear picture.
Yeah, indeed. So that's, of course, a very, very relevant question. Indeed, it's not really in my, let's say, venue. But I mean, what you see is that this sort of, let's say, legislations, the guidelines, those sort of things for geothermal, they are just now start to kind of be formed. So it's not yet as formal and as well described as you see, for instance, in the petroleum sector. But this is something that I think all the countries are talking about it. Even at the EU level. But I mean, also one of my observation when you say about like what is overruling what, in it, my observation is if you see, for instance, a lot of discussions and activities, if I take hydrogen as an example, these are coming, let's say, top down. You know, they're like big plans, and they try to even talk about, let's say, national, European, international scales, and that's how the whole development is being driven. When we look into the heat, most of these sort of, let's say, initiatives are quite bottom up. It starts with the region, it starts with the municipality, and I think kind of ends at the national level. There might be some levels that European and worldwide we can share and exchange ideas and maybe some, let's say, guidelines and things like that. But probably you see that most of these things are going to be driven nationally. That's a little bit my personal opinion, you know, not anything else. But that's a little bit how I'm observing that a lot of these initiatives are quite bottom up, and probably these legislations and those sort of things would also be a little bit driven like that. So I don't know if there will be in the future, instead of API, we will have, I don't know, an AGI for geothermal. I don't know about that, or EGI if we want to make it European. But in that sense, we're gonna wait and see how the market evolves and how this legislation guidelines is going to evolve. So I always give some ideas. Please look into, for instance, the EGEC website. They contain a lot of interesting information about what's happening in Europe, then link to the latest Mineral Act, which also now links very well with our geothermal development. So they share a lot of information there. Hopefully they will be useful for you.
Thank you so much.
Sure.
And yeah, we already answered questions about sharing the presentation. So thank you, Romania. And Frank, you had a question, I believe.
Yeah, thanks for the presentation. On one of the first slides, you also showed the closed loop systems, and at least as I understood, a lot of the operational issues that you mentioned with regard to scaling, corrosion would be reduced with these systems. But of course, I mean, they are not as proven as the open systems yet. So what's your view on the potential of these systems getting more and more applied in geothermal systems and projects?
Yeah, so indeed, that's a kind of the very direct and observable gain from this closed loop system is that you more or less design your geothermal fluid or working fluid yourself. You do it with any properties that you envision to have. You can tune it for the temperature ranges that you have, and all the potential scaling, corrosion, erosion issues, you can actually mitigate it there. Plus, you can also design it in such a way that your pumping power will be minimized. So more or less, if you go into some sort of a thermosiphon effect, that as soon as you heat it up, the kind of the working fluid transport upwards on its own, then you can also minimize your pumping power quite a lot. So those are the gains. But of course, as we said, especially closed loop systems for the deeper system. So now we're talking about kilometers of the closed loop system. These are things that still has to be piloted and evaluated in terms of the performance, especially the long-term performance of these sort of systems. So that is something which is also, I think, an exciting time to to wait and see how these systems will perform. And of course, for the shallower systems, the more this borehole heat exchangers, which often also called ground source heat pumps, these are quite proven technology. So in that sense, closed loop is already a proven technology, but we don't know how they would be performing at this deeper depth, and this additional capex that you have to go deep would actually be paid off. That's the thing that we have to still wait and see how the systems will perform.
Okay, good, thanks.
Yeah, sure, thanks.
Right, and I think that is our time is up. So I want to thank everybody for joining in. If you have any more questions, then feel free to reach out to Pejman or myself. We are back again next month, the 20th of June. SPE Croatia are our hosts, and I hope I get the name right, Dragutin Domitrovic will talk about development of the geothermal business in Croatia, which I believe is going to be slightly hotter than the Netherlands. So we're going to be warming up even more. Right. So thank you very much. Give us 1 or 2 days to load up the recording and the slides, and then we'll send everybody a link with where to download the recording and the PDF of the documents. Pejman, I want to thank you very much for a very interesting talk and conversation, and thanks to all of you for all your questions, and we'll see you again in a month's time. Thank you very much.
Thanks, everyone.